The cosmic horizon is the final frontier of everything we know. Beyond that edge of light and galaxies lies a mystery so profound it has haunted thinkers for centuries. We can map the stars, but the true nature of what lies outside our universe remains our greatest unsolved puzzle. By the end of this journey, you will have explored 25 of the most mind-bending theories ever conceived, from the leading edges of physics to the wildest realms of philosophy, all attempting to answer the unanswerable. We will venture into infinite voids, collide with other dimensions, and question the very nature of reality itself. What do you believe could be waiting in that ultimate darkness? Our first stop is the simplest and perhaps the most unsettling answer to the question. Theory number 1, the infinite universe. Forget an edge, forget a boundary. This idea proposes that our cosmos is simply endless. Space, in this model, is flat and unbounded, stretching on in every direction without limit forever. There is no outside because there is no outside to go to. You could travel for 1 trillion lifetimes at the speed of light and never reach a wall, never cross a border. You will just find more galaxies, more stars, more emptiness in a pattern that never, ever stops. The philosophical weight of this is staggering. If the universe is truly infinite and matter is arranged in a finite number of ways, then everything that can happen does happen. An infinite number of times, somewhere out there in that boundless expanse is another Earth orbiting another sun in another galaxy identical to our Milky Way. On that Earth, there is another you reading these very words, and another, an endless sea of copies, each with minuscule variations stretching into infinity. It is a concept that dissolves our uniqueness into a cosmic statistic. This isn't science fiction, it is a direct mathematical consequence of an infinite, flat universe. The silence beyond our horizon isn't an abyss, it is simply more of the same, a fractal reality repeating its patterns across an eternal grid forever. But infinity is not the only shape reality can take. Theory number 2 offers a different and scientifically profound answer: the multiverse of cosmic inflation. This is not a vague philosophical idea, but a direct prediction from our most successful theories of the universe's explosive birth. The concept, pioneered by physicists like Alan Guth and Andrei Linde, suggests that the Big Bang was not a unique, one-time event. Instead, it was more like a local bubble nucleation within a far vaster, eternally inflating cosmic field. Picture a pot of water just beginning to boil. The roiling surface is the inflating field, a seething energy landscape. Everywhere across it, tiny bubbles spontaneously form and rapidly expand. Our entire observable universe is just one of those bubbles, a single island of stable spacetime that stopped inflating and cooled into the cosmos we know. But outside our bubble wall, the greater inflationary field continues its relentless, exponential expansion, creating new bubbles endlessly. This is a frothing cosmic foam, where each bubble is its own separate universe, forever drifting apart, isolated within an unobservable sea of hyper-fast expansion. The staggering implication is that each of these bubble universes could be a unique cosmic experiment. When a bubble forms, the fundamental forces within it can freeze into place randomly. In our bubble, gravity is weak, atoms can form, and stars can shine. But in another bubble, gravity might be 1,000,000 times stronger, instantly crushing any structure. In another, electromagnetism might be too feeble to bind atoms. Some bubbles might have 4 dimensions of space, others 10. The constants of physics we consider sacred and immutable could be nothing more than local bylaws in our particular cosmic neighborhood. We are not just looking at more stars beyond a horizon. We are potentially looking at an infinity of entirely different realities, each with its own unique laws of nature, most of them utterly sterile and inhospitable to life as we could ever recognize it. Our universe's fine-tuning for life becomes less of a miracle and more of a statistical inevitability, given an infinite number of random cosmic draws. Yet the inflationary multiverse is not the only way to imagine a sea of other worlds. A completely different kind of reality emerges from the bizarre rules that govern the very small. Theory number 3, the quantum many-worlds interpretation. This idea, first proposed by physicist Hugh Everett in the 1950s, suggests that our universe is not a single linear timeline. It is a constantly branching tree of every possible reality, splitting apart at every single quantum event. The key difference from the inflationary bubble multiverse is profound. The inflationary multiverse gives us separate universes with different fundamental laws of physics. The many worlds interpretation gives us an infinite number of universes that all share the exact same laws but diverge in their histories based on chance. It works like this. In the quantum realm, particles exist in a haze of probability called a superposition. An electron is not simply here or there, it is both places at once with a certain probability for each location. The classic thought experiment is Schrödinger's cat, a creature trapped in a box with a quantum device that may or may not release poison. According to traditional quantum mechanics, the cat is both alive and dead until someone opens the box and looks, forcing the system to choose one definite state. Everett offered a radical alternative. He proposed that the act of observation does not force a choice. Instead, the universe itself splits. In one new branch of reality, the observer opens the box and finds a living cat. In another, completely separate but equally real branch, the observer opens an identical box and finds a dead cat. Both outcomes happen. Both observers go on with their lives completely unaware of the other. Now apply this to every single quantum event, every particle collision, every radioactive decay, every choice made by every conscious being. At each of these trillions upon trillions of junctures, the universe fractures, creating new, parallel timelines for every possible outcome. What lies beyond our cosmic horizon in this view is not just more space. It is the sum total of every road not taken, every chance event that went another way, an infinite tapestry of what-ifs woven into the fabric of reality. In one universe, you turned left on your way to work today. In another, you turned right. In one, the dinosaurs never went extinct. In another, humanity never discovered fire. The tree of possibilities is endless, with our lived experience representing just one single, meandering twig on an infinite, ever-growing tree. This means that every possible version of history, no matter how strange or improbable, is playing out somewhere in this vast quantum ensemble. The silence beyond the stars is not empty, it is humming with the echoes of every possibility that ever was or ever could be. The quantum multiverse suggests a reality that branches with every choice. But what if our entire universe is just a single page in a much larger cosmic book? Theory number 4, the brain multiverse, emerges from the deepest mathematical trenches of string theory, and it proposes a reality stranger than any branching timeline. In this view, our familiar 3 dimensions of space are not all there is. The universe we perceive is a 3-dimensional membrane, or brain for short, floating within a higher dimensional arena called the bulk. Imagine our entire cosmos, every galaxy and star, as a vast, impossibly thin sheet of paper. That sheet is drifting in a space that has more dimensions than we can see or move through. We are stuck on the brain, like ants confined to the surface of that paper, completely unaware of the immense volume around us. Other universes could simply be other sheets, other brains, floating parallel to our own in this higher dimensional bulk. They could be inches away in a direction we cannot point to, hosting alien forms of matter and energy governed by different physical laws. The most dramatic version of this idea is the ekpyrotic model, which reimagines the Big Bang not as a fireball from a singularity, but as the result of a collision. Picture two of these cosmic sheets drifting silently in the dark bulk over eons. They slowly draw together, and when they finally meet, the impact releases a titanic flood of energy, heating and expanding each brane to create a new hot universe. In this model, our cosmic beginning was a quiet, almost gentle touch in a higher dimension, whose echoes we still see as the afterglow of creation. But how could we ever detect these neighboring branes? The key might be gravity. In many brane world models, the other fundamental forces, like electromagnetism, are glued to our brain. They cannot leave the sheet. Gravity, however, is different. It is so weak because it is not confined. It can leak off our brain, spreading out into the bulk, which dilutes its strength in our three-dimensional world. This leakage could be our one window into the greater bulk. Ripples in gravity, like those from colliding black holes detected by observatories like LIGO, might carry subtle fingerprints of their journey through extra dimensions. The thought is dizzying. That faint gravitational tug you feel keeping your feet on the ground is not just a force within our universe, but a whisper escaping into a hidden, higher dimensional sea, where other cosmic islands may be drifting just out of sight. But the idea of a universe with a definitive end is not the only possibility. Theory number 5, the cyclic universe, offers a vision of cosmic immortality, an endless rhythm of death and rebirth that stretches back forever and forward into eternity. This concept suggests our universe is not on a one-way trip to cold, dark emptiness. Instead, it is caught in an infinite loop, a cosmic heartbeat. In its most classic form, the universe expands from a big bang, reaches a maximum size, and then gravity, pulling all matter back together, wins the battle. Every galaxy, every star, every atom is drawn back into a single, unfathomably dense point, a big crunch. But instead of marking a final end, this singularity becomes the seed for the next big bang. The universe collapses, rebounds, and explodes outward again in a new cycle. What lies beyond our cosmic horizon in this model is not another place, but another time. It is the future of our own universe, destined to contract and be reborn. The space between cycles is not an empty void, but a state of near-infinite density and temperature, a cosmic reset button that erases the old universe and prepares the canvas for the next. In this eternal return, every configuration of matter might eventually repeat. The same galaxies could form, the same stars could ignite, and the same planets could give rise to life over and over again across eons. It is the ultimate phoenix, rising from its own ashes in a cycle without beginning or end. A modern and startling twist on this idea comes from the renowned physicist Roger Penrose with his theory of conformal cyclic cosmology. Penrose proposes a cycle not of collapse and explosion, but of a graceful, infinite fading and renewal. In his vision, our universe will expand forever, as the dark energy models predict. But over trillions upon trillions of years, all matter will eventually decay, black holes will evaporate, and the universe will become a sea of featureless radiation, expanding into a state of perfect uniformity with no discernible scale or time. In this strange, stretched-out end, Penrose sees a new beginning. He argues that this vast, empty, timeless state can be mathematically conformed or rescaled to match the hot, dense, uniform state of the next universe's Big Bang. The end of time in one cycle becomes the beginning of time in the next. It is as if the final note of a symphony, drawn out into an infinite, silent drone, becomes the first note of the next symphony when played at a different pitch. In this model, the evidence of previous universes might literally be imprinted on our own. Penrose suggests that concentric rings in the cosmic microwave background, the faint afterglow of our own Big Bang, could be the gravitational shockwaves from the collision of supermassive black holes in the universe that came before ours. We might be living in just one episode of an infinite series, with faint echoes of the previous chapter still reverberating in the sky. The horizon we see is not a boundary in space, but a window into the deep future of our own cosmos, a future that is also the dawn of another. The idea of a cosmic cycle suggests a universe with a deep, hidden structure, but what if that structure is an illusion? Theory 6, the holographic universe, proposes a truth so radical it redefines the nature of reality itself. This is not about literal holograms like those on a credit card. It is a profound principle emerging from the study of black holes, suggesting that all the information that makes up our three-dimensional world, every star, every planet, and every one of us, is actually encoded on a two-dimensional surface at the very boundary of space. Think of a movie. The rich, three-dimensional world you see on the screen is not actually inside the television. It is projected from a flat, two-dimensional source, the film strip or digital file. The holographic principle argues our universe works the same way. The three-dimensional cosmos we experience could be a magnificent projection. The real action, the fundamental code of reality, is written on a distant, two-dimensional shell that surrounds us. So what lies outside our cosmic horizon in this model? The answer is not more space, but the higher dimensional realm where the projector exists. We are the movie. The outside is the projector room. This mind-bending idea has firm roots in black hole physics. When an object falls into a black hole, according to the laws of thermodynamics, the information about that object cannot be destroyed. But where does it go? Physicists like Leonard Susskind and Gerard T. Hooft realized that the information could be preserved, not within the black hole's three-dimensional volume, but on its two-dimensional event horizon, the point of no return. The surface area of the horizon, they argued, holds all the information about everything that has ever fallen in, like a cosmic hard drive. Extend this logic to the entire universe. The cosmological horizon, the farthest point we can see, might act in a similar way. It could be a vast, spherical screen upon which the information for every event within our observable universe is perfectly stored. Our reality, with all its depth and texture, is then a holographic reconstruction from that data. This means the world you see and touch, with its solidity and volume, is a kind of exquisite illusion. The true, fundamental reality is a flat, information-rich surface at the edge of everything. The force of gravity and the fabric of space-time itself might not be primary forces, but emergent phenomena, side effects of this deeper information processing. So when we peer to the edge of the cosmos, we are not looking out into an abyss. We are, in a sense, looking at the source code. The great darkness is not empty, it is the screen, and we are the breathtaking image it displays. But if our reality is a projection, what is the nature of the projector? This brings us to theory number 7, a modern idea that has captured the imagination of philosophers, tech billionaires, and physicists alike. The simulation hypothesis, it proposes a startling possibility. Our universe, with all its cosmic grandeur and intimate detail, is not fundamental. It is a sophisticated simulation, a kind of ultra-advanced video game, being run on the hardware of a civilization immeasurably more advanced than our own. In this view, the stars are not balls of plasma, but meticulously rendered pixels. The laws of physics are not immutable truths, but the programmed rules of the simulation's engine. And what lies beyond our cosmic horizon is not more simulated space, but the limits of the simulation's processing power, or perhaps the firewall separating our instance from others. The philosopher Nick Bostrom formalized this idea into a compelling trilemma, a set of 3 possibilities. He argued that at least one of these statements is almost certainly true. First, that virtually all civilizations at our level of technological development go extinct before they can create advanced simulations. Second, that any advanced civilization loses all interest in creating simulations of their ancestors. Or third, that we are almost certainly living in a simulation. The logic is based on a simple extrapolation. If even one civilization survives to a post-human stage and retains an interest in its history or in running ancestor simulations for research or entertainment, they would likely have the computational power to create vast numbers of such simulations, each populated with conscious simulated beings. The number of simulated minds would quickly dwarf the number of original biological ones. Therefore, if you are a conscious being, the odds are overwhelmingly high that you exist in one of the many simulations, not in the base reality. The implications are profound. The outside of our universe is not a void or a higher dimension, but a physical reality belonging to the simulators. Their universe, the base reality, would have its own laws of physics which might be utterly alien to our own. Their hardware could be a planet-sized quantum computer or something our minds cannot even conceptualize. Glitches in our reality, like déjà vu or mysterious quantum effects, could be seen as minor processing artifacts or background code. The entire history of our cosmos, from the Big Bang to this very moment, could be a narrative script, a generated world for study, or even a form of entertainment. This theory reframes every mystery. The search for a unified theory of physics becomes the search for the source code. The fine-tuning of the universe for life is no longer a lucky accident, but evidence of intentional design parameters. And our own drive to create virtual worlds, from simple games to complex virtual realities, might be a faint echo of the process that created us, a hint embedded in the simulation itself. Are we the creators, or are we the created, peering out at a horizon that is, in truth, the edge of our own cage? The simulation hypothesis makes us question the very substance of our reality, but another theory suggests the answer to what lies outside is not a computer, but a cosmic tomb-turned-womb. Theory number 8, black hole cosmology. This is the provocative idea that our entire universe, every galaxy and star we see, exists inside a black hole belonging to a much larger parent universe. In this model, the Big Bang was not the beginning of everything. It was the violent birth of a new reality from the death of an old one. When a massive star collapses in that parent cosmos, it forms a singularity, a point of infinite density hidden behind an event horizon. But what if that singularity does not mark an end? What if it is a bridge? Some physicists, like Nikodem Poplawski, have explored mathematical models where the crushing collapse inside a black hole does not stop at a point. Instead, the extreme torsion or twisting of space-time causes a rebound and explosive reversal. The singularity becomes a white hole, spewing out all the matter and energy that fell in, but into a new, separate region of space-time. Our Big Bang, in this view, was the white hole eruption from a black hole collapse in another universe. So what lies beyond our cosmic horizon? It is not empty space. It is the event horizon of the black hole that contains us. We are living inside the ultimate cosmic Russian doll. Our observable universe is the expanding fireball on the inside of a boundary we can never cross. The parent universe, with its own stars and galaxies, exists forever outside our event horizon, forever out of reach. This leads to a dizzying fractal possibility. Every black hole that forms in our universe could, in turn, be the seed for a brand new cosmos within it. Our own night sky might be dotted with the birth cries of entire universes, each hidden behind the dark veil of a singularity. A star dies here and a cosmos is born there. This creates a potentially infinite cascade of realities, a cosmic matryoshka of unimaginable scale. The theory even offers a potential explanation for the arrow of time. The relentless expansion of our universe and our perception of time moving forward could be an inheritance from the initial outward explosion from the white hole singularity. We are living in the aftermath of that single, irreversible event. While this remains a speculative idea, it is grounded in the twisting equations of Einstein's general relativity, and it provides a stunningly elegant symmetry. Death gives birth, a collapse becomes an expansion. The darkest objects in our sky might not be endpoints but gateways, and our entire existence might be the brilliant, unfolding interior of something a civilization in a parent universe simply calls a black hole. The black hole cosmology suggests our reality is nested within another. But what if the ultimate nesting is not of space but of logic itself? Theory number 9, the mathematical universe hypothesis proposed by physicist Max Tegmark, offers perhaps the most radical and austere answer of all. It states that our physical reality is not just described by mathematics, it is mathematics. The universe is a mathematical structure, and we are self-aware patterns within it. In this view, the stars are not made of plasma, but of mathematical relationships. Gravity is not a force, but a curvature described by equations. What we perceive as the physical world is simply a particular, complex mathematical object playing out its inherent properties. So what lies beyond our cosmic horizon? The answer is not more space or other dimensions, but other mathematical structures. Tegmark organizes the concept of a multiverse into 4 levels. Level 1 is simply the infinite universe we discussed, where our observable cosmos is just a tiny patch in a vast, endless expanse of similar space. Level 2 introduces the bubble universes of eternal inflation, where different regions have different physical constants. Level 3 is the quantum many worlds, where every possible outcome of every event occurs in a branching tree of realities. But it is Level 4 that is truly staggering. The Level 4 multiverse contains all mathematical structures that are logically consistent. Every possible set of equations that can describe a self-consistent reality exists somewhere in this ultimate ensemble. Our universe, governed by the specific rules of general relativity and quantum field theory, is just one entry in an infinite library of mathematical possibilities. In another structure, 2 plus 2 might equal 5. In another, circles might have corners. In another, time might flow in loops or exist in multiple dimensions. These are not just different physics, they are different logics, different geometries of existence that our brains, wired for this particular mathematical structure, cannot even begin to visualize. The outside of our universe is not a place, but the transcendent realm of all abstract mathematical truth. We are not looking out at a dark void, but at the boundary of our own equation. This means that every universe that can exist does exist simply by virtue of being mathematically possible. The fine-tuning problem vanishes because every possible tuning exists in some structure. The search for a theory of everything becomes the search for which specific mathematical object we happen to inhabit. It is a breathtaking and humbling idea. Our entire cosmos, with all its beauty and terror, is reduced to a single point in an infinite landscape of pure abstraction. We are not just stardust, we are a fleeting thought in the mind of a timeless, impersonal mathematician that is mathematics itself. Yet another bridge between worlds emerges from the very equations that predict black holes. Theory 10, the white hole and wormhole connections. If a black hole is a point of no return where gravity is so strong that nothing, not even light, can escape, then a white hole is its theoretical opposite. It is a point of no entry, a cosmic fountain that only spews matter and energy out, violently rejecting anything that tries to fall in. Now, imagine that our Big Bang was not a unique beginning, but the explosive eruption of a white hole. In this scenario, all the matter and energy that constitutes our universe was not created from nothing, but was expelled from another region of space-time, perhaps from a black hole in a parent cosmos. Our entire history is the aftermath of that single, irreversible outburst. This idea creates a stunning symmetry, linking the death of one reality to the birth of another. But the connection might be more than just a one-way street. The same mathematics that describes black holes and white holes also allows for a shortcut, a tunnel that could link them directly, an Einstein-Rosen bridge, more popularly known as a wormhole. Picture the fabric of spacetime as a vast sheet of paper. If you want to travel from point A to point B on the sheet, you must travel across the surface. But if you could fold the paper, bringing those 2 points together, you could punch a hole through, creating a tunnel that connects them instantly. A wormhole is that tunnel through the higher dimensional bulk of space. In theory, one mouth of the wormhole could be a black hole in one universe, and the other mouth could be a white hole in another, creating a cosmic umbilical cord between realities. You could, hypothetically, fall into the black hole in one cosmos and be violently ejected from the white hole in another, having traversed an impossible distance in a heartbeat. The visual is captivating, a luminous tunnel of warped space connecting 2 glowing spheres of universe. However, the physics is brutally unforgiving. The primary challenge is stability. The kind of wormhole predicted by Einstein's equations would be incredibly unstable. It would snap shut the instant anything tried to pass through, crushed by its own immense gravitational forces. To hold it open, to make it traversable, you would need a form of matter with negative energy density, something that creates a repulsive gravitational effect to counteract the collapse. We have hints that such exotic matter might exist in tiny quantities in quantum fields, but to stabilize a wormhole large enough for anything to pass through would require astronomical amounts of it, far beyond any technology or phenomenon we can conceive. Furthermore, even if you could enter, the tidal forces near the center or the intense radiation would likely destroy any information or object long before it reached the other side. So while wormholes are a beautiful theoretical possibility, a cosmic subway system linking disparate realities, they remain firmly in the realm of mathematical speculation. They are a reminder that the universe's blueprints may contain passages we can see in the equations, but which the harsh laws of physics forever bar us from walking. The stability of wormholes is a monumental challenge, but what if our entire universe required no such engineering? Theory 11, the universe as a quantum fluctuation, suggests that everything we know, every galaxy and star, is the result of the ultimate cosmic free lunch. This idea emerges from the bizarre rules that govern the realm of the very small, where the concept of nothing is anything but empty. In quantum field theory, the vacuum of space is not a placid, static void. It is a seething, bubbling sea of potential, alive with activity. At the tiniest scales, pairs of particles and antiparticles constantly wink into existence, borrowing energy from the vacuum itself, only to annihilate each other and vanish back into nothingness a moment later. These are called virtual particles, and their fleeting dance is a proven feature of our reality, responsible for subtle effects like the Casimir force. Now stretch this concept to its absolute limit. If a particle pair can pop out of nowhere, why not an entire universe? Some physicists like Edward Tryon proposed exactly that. He suggested our cosmos began as a random, colossal quantum fluctuation in a primordial, timeless void. In this view, the total energy of the universe is precisely zero. All the positive energy bound up in matter and radiation is perfectly balanced by the negative gravitational energy of space itself. The universe, therefore, is the ultimate zero-sum event, a fluctuation that borrowed nothing from nothing and owes nothing back. It simply is. What lies beyond our cosmic horizon, then, is not another place or a higher dimension, but the eternal, featureless quantum foam from which our bubble of spacetime spontaneously nucleated. This is a reality of pure chance on a cosmic scale. Universes could be popping in and out of existence all the time, like bubbles in a vast, uncaring ocean of nothingness. Most would be tiny, ephemeral things collapsing back into the vacuum in an instant, but by sheer statistical chance, once in an eternity, a fluctuation might be large enough and stable enough to undergo a process like inflation, ballooning to an immense size and cooling into a long-lived cosmos like our own. We are that one in an infinity roll of the dice, a universe that won the quantum lottery and got to stick around. The silence beyond the stars is the hum of infinite possibility, where the fabric of reality itself is in a permanent state of creative frenzy, birthing and dissolving entire worlds in moments too short to measure. Our majestic, ancient cosmos might be nothing more than a particularly persistent ripple in an endless, silent sea of nothing. Physics provides the structure, but philosophy asks the deeper question of what that structure must contain. Theory 12, the ultimate ensemble, championed by physicist David Deutsch, offers a breathtakingly expansive answer. Deutsch argues that every single physically possible world is not just a mathematical abstraction, but is just as real as our own. In his view, the multiverse is not a collection of similar bubble universes or branching timelines. It is the exhaustive set of all realities that do not contain logical contradictions. What lies beyond our cosmic horizon, then, is not just more space, but every single variation of reality that the laws of physics allow. This is the multiverse in its most unconstrained, maximal form. It includes the inflationary bubbles with different constants and the quantum branches of our own history, but it goes infinitely further. It contains universes where gravity is 1,000 times stronger, where light moves at a walking pace, where time has 2 dimensions and flows in a spiral. It includes worlds made entirely of crystal or of sentient gas clouds, or where the concept of solid matter never emerged. It contains a reality where the Roman Empire never fell and developed interstellar travel, and another where Earth was never struck by the asteroid, leaving dinosaurs to evolve into intelligent, tool-using beings. Every novel, every daydream, every myth that does not violate fundamental logic exists somewhere in this ultimate ensemble as a concrete, physical reality. The key distinction here is between what is physically possible and what is logically impossible. A universe where 2 + 2 = 5 is logically impossible within standard arithmetic, so it is excluded. But a universe where water is not wet or where stars think could be physically possible under a different set of emergent laws, and thus finds its place in the ensemble. This idea moves beyond the predictive frameworks of inflation or quantum mechanics into a profound philosophical stance about existence itself. It claims that reality cannot be capricious. It cannot choose one possibility and discard the others. If something can happen, it does happen, somewhere in the vast tapestry of all that is possible. Our universe feels unique and special to us, but in the ultimate ensemble, it is merely one page in an infinite library, surrounded by stories so alien we could never comprehend their plots. We are not living in the only reality, or even a particularly likely one. We are simply living in a reality compatible with our own existence, a single thread in a fabric woven from every conceivable thread. The ultimate ensemble suggests a reality of infinite possibilities, but it remains a cold, logical architecture. What if the cosmos is not just a collection of objects, but a living, thinking entity? Theory 13, the universe as a conscious entity, introduces a profound philosophical shift. This is the ancient idea of panpsychism, reimagined for the modern age. Panpsychism proposes that consciousness is not a rare product of complex brains, but a fundamental property of the universe like mass or charge. In this view, everything from a quark to a galaxy possesses some minute degree of inner experience, some faint spark of subjective feeling. A rock's consciousness would be unimaginably simple, a bare whisper of existence, while a human brain integrates trillions of such whispers into the rich symphony of self-awareness we experience. So what lies beyond our cosmic horizon? It might not be more space, but deeper layers of a universal mind. The entire cosmos could be a vast, integrated network of experience, a single conscious entity on a scale so grand we are merely neurons in its thoughts. Our individual awareness might be like a single cell in a body, utterly unaware of the greater organism it helps to constitute. The stars are not just burning gas, but perhaps nodes in a cosmic neural network, their gravitational links forming the synapses of a mind thinking thoughts that span billions of years. A modern scientific framework that lends credence to this idea is Integrated Information Theory, or IIT. Developed by neuroscientist Giulio Tononi, it attempts to mathematically quantify consciousness. The theory argues that consciousness arises from a system's ability to integrate information. The more interconnected and differentiated a system is, the higher its degree of consciousness, or phi. Apply this to the universe itself. The cosmic web of galaxies, connected by gravity and entangled by quantum fields, forms a system of staggering complexity. Its phi value, if we could calculate it, might be astronomically high, suggesting the cosmos itself could possess a form of consciousness utterly alien to our own. Its thoughts would not be words or images, but the slow, majestic dance of galaxies, the birth and death of stars, the very unfolding of physical law. Our lives, our histories, could be fleeting patterns within that vast, eternal contemplation. The darkness beyond the horizon is not empty, but the boundary of our local awareness within a greater, dreaming mind. We are not just inhabitants of the universe, we are fragments of its consciousness, temporarily isolated, peering out at the rest of ourselves. The idea of a conscious cosmos suggests a universe alive with thought, but another theory from the heart of physics presents a reality frozen in a single, eternal moment. Theory 14, the static universe, also known as eternalism or the block universe. This is not a theory about what the universe is made of, but how it exists in time. It emerges directly from Einstein's theory of relativity, which forever welded space and time into a single, four-dimensional fabric called spacetime. In this view, the past, present, and future are not a river flowing from one to the next. They are all equally real, all existing at once. The universe is not becoming, it simply is. Imagine the entirety of existence, from the Big Bang to the farthest future, as a gigantic loaf of bread. Each slice of that loaf is a single moment in time, a three-dimensional snapshot of the entire cosmos at that instant. Your birth is on one slice. You reading this now is on another slice, somewhere toward the middle. Your future, in whatever form it takes, is on slices further down the loaf. In the block universe, all these slices exist simultaneously, stacked together into a solid, unchanging four-dimensional block. Your life is not a story being written, but a world line, a thread woven through the block from one end to the other, already complete. This shatters our most intuitive experience of time. The feeling that the past is gone and the future is not yet real is, according to this model, a powerful illusion generated by our consciousness as it moves along our world line. We are like a tiny ant crawling along the groove of a vast cosmic record. We experience each note as it passes, but the entire symphony is already etched into the vinyl, fixed and unchangeable. So what lies beyond our cosmic horizon in this model? The answer becomes deeply strange. Beyond might not be a spatial direction at all. If we could somehow step outside the four-dimensional block of our universe, we would not see more space. We would see the entire history and future of our cosmos laid out as a single, frozen sculpture. We could look down and see dinosaurs roaming, and look up to witness the sun's death, all existing in a permanent now. Furthermore, the block universe idea opens the door to other blocks. Just as our universe is one static four-dimensional object, there could be other, completely separate blocks of space-time with entirely different histories and futures, floating in some higher dimensional manifold. They wouldn't be before or after ours, they would just be other configurations, other sculptures in the gallery of all possible spacetimes. This view is called eternalism, and it stands in stark contrast to presentism, the philosophy that only the present moment is real. Presentism aligns with our gut feeling, but it struggles to reconcile with relativity, where the concept of a universal now breaks down across vast distances. Eternalism, while counterintuitive, is what the mathematics of our best theory of spacetime strongly suggests. It means every moment of joy, every moment of sorrow, every triumph and tragedy in cosmic history is forever preserved, not as a memory or a possibility, but as a permanent fixture in the architecture of reality. The great expanse we peer into is not an empty stage waiting for events to happen. It is a magnificent finished tapestry, and we are simply discovering the pattern thread by thread. Our experience of a solid, four-dimensional block suggests a fixed reality. But what if that block is built from something far more fundamental than matter or energy? Theory 15, the universe as information, proposes that the most basic ingredient of existence is not a particle or a field, but a bit. This is the philosophy of it from bit, pioneered by physicist John Archibald Wheeler. He suggested that every particle, every force, and every event in the cosmos ultimately derives its existence from binary yes or no answers, from the act of observation that calls physical reality into being. In this radical view, matter is not primary, information is. The cosmos is not a thing that contains information like a book contains words. The cosmos is the information itself. It is a cosmic computation, a vast, ongoing calculation whose output is the reality we perceive. Think of a breathtakingly realistic video game. The mountains, the rivers, the characters you see on screen are not made of dirt, water, or flesh. They are made of data, of ones and zeros processed by the game's engine according to a set of rules. The digital physics interpretation suggests our universe operates on a similar principle, but at the most fundamental level possible. The stars are not fiery plasma, but patterns in a cosmic program. Gravity is not a force, but an algorithm governing the relationship between data points. Even the flow of time could be the sequential processing of these informational operations. This leads to a startling possibility about what lies beyond our cosmic horizon. If we are living in a simulation, the outside is the computer running the code. But in a more profound sense, even if ours is the base reality, the outside could be the transcendent realm of pure information, the source code from which physics emerges. The great darkness at the edge of the universe might not be empty space, but the boundary of the simulation's rendered distance, or the limit of the computational process for this particular region. Proponents of this view point to tantalizing clues within physics itself. The laws of thermodynamics which govern energy are fundamentally about information. The entropy of a system is a measure of its informational disorder. Black holes, those ultimate sinks of matter, have entropy proportional to the area of their event horizons, suggesting that information is stored on a surface, not within a volume, echoing the holographic principle. Even quantum mechanics, with its probabilities and observer-dependent collapses, behaves less like a description of solid objects and more like a description of data being retrieved or realized. So what are we in an informational universe? We are self-aware patterns within the data, complex algorithms that have developed the capacity to observe and process the very information that constitutes them. Our quest to understand the cosmos is the program attempting to read its own source code. Every scientific experiment is a query to the universe's database. Every observation is a measurement that collapses a wave of probability into a definite bit of reality. This framework makes the fine-tuning of the universe for life feel different. It is not a lucky accident or a statistical fluke in a multiverse, but perhaps evidence of elegant, optimized code, written with certain parameters to allow for complex structures like us to emerge. The silence beyond the stars is not an emptiness to be feared, but the quiet hum of the universe's processor, carrying out calculations on a scale we can scarcely fathom, rendering reality one bit at a time. The information-based universe feels like a silent, digital computation, but another model proposes a far more dramatic and physical genesis. Theory 16, the ekpyrotic and colliding brain model, offers a spectacular vision of creation not from a singular point, but from a shattering impact in a hidden dimension. This is a specific, elegant form of cyclic cosmology where our universe is a three-dimensional membrane or brain floating in a higher dimensional space. The story begins not with a bang but with a silent drift. Two of these immense parallel cosmic sheets, each potentially hosting its own universe, float in the dark bulk, drawn together by a faint force across the gap. They approach with an inevitability measured in eons, a slow-motion dance set to the clock of higher dimensional physics. When they finally meet, the collision is not a destructive crash but a creative one. The kinetic energy of the impact is instantly converted into a searing flood of radiation and matter, heating the brains to an unimaginable temperature. This is our Big Bang, a fiery rebirth born from contact. The brains then rebound, pushing apart, and the immense energy deposited on them begins to expand and cool, forming the particles, atoms, and eventually the galaxies we see today. Our universe is the aftermath glowing on the surface of that wounded brain, but the cycle does not end there. After expanding for billions of years, the energy dissipates, and the attractive force between the brains once again pulls them together. The universe we know contracts not into a point but toward another inevitable collision, which will trigger the next cosmic cycle. We are living in the calm, expansive phase between two titanic collisions, our entire history a temporary echo of that primordial crash. This model elegantly tackles several cosmological puzzles. It provides a natural explanation for the uniformity of the cosmic microwave background, the afterglow of creation. Because the colliding brains are nearly uniform and infinite, the heat from their impact is spread evenly, leading to the remarkably consistent temperature we observe across the sky. It also potentially explains the origin of the large-scale structures, the great walls and voids of galaxies, as faint imprints or wrinkles from the brain collision itself, cosmic fingerprints left in the fire. The visual is breathtaking, two vast, shimmering planes of reality moving through a hyper-dimensional night, their meeting point erupting into a storm of light and matter that blossoms into a whole new cosmos. It suggests a universe with a rhythm, a heartbeat of collision and separation that may have been ticking forever, with our existence a single pulse in an endless, grand and violent dance. The promise of the ekpyrotic model is that it leaves a distinct signature in the sky, a cosmic fingerprint of that ancient collision. Proponents of the theory predict that the titanic, sheet-like crash would have generated gravitational waves, ripples in space-time itself. But unlike the violent, chaotic waves predicted by some inflationary models, the ekpyrotic collision would produce a very specific, much fainter spectrum. These waves would imprint a unique, telltale pattern on the polarization of the cosmic microwave background, that faint afterglow from the universe's hot youth. It would be a subtle, swirling signature etched into the oldest light we can see, a direct message from the moment of creation. Finding that specific pattern would be like discovering the skid marks from the cosmic collision that birthed us, a smoking gun for the brain world hypothesis. Yet so far, despite our most sensitive telescopes scanning the microwave sky, this predicted signal has remained elusive. Its absence does not disprove the theory, but it means the model's most dramatic prediction is still waiting for confirmation. This search highlights the high stakes of modern cosmology, where scientists scrutinize the faintest whispers of radiation from the edge of time, hoping to decode whether our beginning was a lonely inflation or a shattering impact in a hidden dimension. The theory also faces significant theoretical hurdles that keep it in the realm of compelling speculation. One major challenge is the initial conditions problem. For the cyclic model to work seamlessly, the two brains must start almost perfectly parallel and flat before their collision. They need to be aligned with extraordinary precision across their entire, possibly infinite, expanse. Achieving this setup naturally, without invoking a kind of cosmic fine-tuning of its own, is a puzzle that physicists are still wrestling with. It raises the question, what set up that perfect, silent approach in the first place? The model elegantly replaces the singularity of the Big Bang with a collision, but it may simply push the mystery of beginnings one step further back into the history of the bulk. This brings us to the heart of a great scientific debate, a quiet battle of cosmic origins fought in equations and observational data. On one side stands the reigning champion, cosmic inflation, which describes a universe that underwent a period of unimaginably rapid expansion from a single ultra-dense point. Inflation elegantly explains the large-scale smoothness and flatness of our universe, and it predicts a different, stronger spectrum of primordial gravitational waves. On the other side stands the ekpyrotic challenger, with its vision of a cyclical, colliding universe born from a higher dimensional event. Both theories can explain the key features we see in our cosmos today, like the uniform microwave background. The battle is won or lost in the details, in the specific patterns left in that ancient light, and the mathematical elegance of each framework. For now, inflation remains the dominant paradigm, supported by a wider body of evidence and integration with particle physics. But the ekpyrotic model stands as a powerful and beautiful alternative, a reminder that our universe's first moment might not have been an explosion from nothing, but a rebirth from contact with another world entirely. The silence we perceive may hold the fading echo of a crash we can almost hear. The battle between inflation and ekpyrosis is a search for our true origin, but another theory questions whether we have any origin at all. Theory 17, the Boltzmann brain paradox, is perhaps the most unsettling idea in all of cosmology. It is a thought experiment that emerges not from the edges of space, but from the fundamental laws of thermodynamics, and it suggests that our most cherished certainty, our own existence, might be the ultimate cosmic illusion. The paradox is named for Ludwig Boltzmann, the 19th century physicist who helped define entropy, the measure of disorder in a system. The second law of thermodynamics states that entropy always increases, that the universe moves from order to disorder. Yet Boltzmann realized that in a truly infinite or eternal universe, even the most wildly improbable events must happen eventually, given enough time. Random thermal fluctuations in the chaotic soup of particles could, by sheer accident, assemble anything, no matter how complex, given an eternity. A perfect statue could spontaneously form from scattered dust. A printed copy of a Shakespearean sonnet could assemble letter by letter from a whirlwind of ink. And in the most extreme case, a fully formed, conscious human brain, complete with a lifetime of false memories, could blink into existence from the void. This is a Boltzmann brain. It would not be born, it would not evolve. It would simply materialize, fully operational, convinced it is a real person living in a real world, when in fact it is a momentary accident in an endless sea of chaos. The terrifying implication of the paradox is this: in an infinite, eternal universe headed for maximum disorder, the random fluctuation that creates a single, self-aware brain is astronomically more probable than the fluctuation that creates an entire, ordered, 13.8 billion-year-old cosmos with galaxies, planets, and billions of evolved conscious beings. It is far easier for chaos to assemble one thinking entity with a convincing hallucination than to assemble the staggeringly complex and low-entropy history of our universe. Therefore, if our universe is infinite and eternal, the statistical argument suggests you are vastly more likely to be a Boltzmann brain, a fleeting phantom with fabricated memories, than a real person who evolved on a real planet. What lies beyond our cosmic horizon in this view is not other universes or higher dimensions, but the overwhelming statistical truth that our reality is almost certainly not real. The stars you see, the ground beneath your feet, the very narrative of your life, could be a detailed, convincing illusion generated by a brain that formed a moment ago and will dissolve a moment from now. This paradox is not just a philosophical curiosity, it is a serious crisis for certain cosmological models. any theory that predicts an eternal or infinitely large universe, like some versions of eternal inflation or a cyclic model with no beginning, must grapple with the Boltzmann brain problem. If such models are correct, then Boltzmann brains should outnumber ordinary observers like us by an unimaginable factor, making our existence as evolved beings a statistical absurdity. The fact that we observe a coherent, low-entropy past is therefore evidence against those models. It forces cosmologists to seek theories with a definite beginning and a clear arrow of time, models that naturally explain why we find ourselves in an ordered cosmos and not as transient ghosts in a thermal bath. The Boltzmann brain paradox holds up a mirror to reality and asks a devastating question. Are we the product of a grand cosmic history, or are we just a random thought in the mindless chaos of eternity, a mirage that believes its own reflection? The sheer horror of the Boltzmann brain paradox has not been ignored by cosmologists. In fact, this philosophical nightmare acts as a powerful filter, a tool that forces our theories of the cosmos to become more precise and less fanciful. To resolve the paradox, scientists must find ways to make evolved observers like us more statistically likely than a random, disembodied brain. This often means constraining the future of the universe, taming the idea of eternity itself. One leading proposal focuses on the nature of our cosmic end. If the universe expands forever under the influence of dark energy, as current evidence strongly suggests, the nature of that expansion is critical. If dark energy remains a constant described by Einstein's cosmological constant, the universe will eventually approach what is called a de Sitter space. This is a bleak, empty future where the expansion accelerates so much that even atoms are torn apart, leaving behind a cold, featureless void. Crucially, in a pure de Sitter space, the vacuum has a temperature and thermal fluctuations can still occur. But the rate at which complex structures like brains could randomly fluctuate into existence is incredibly, unimaginably slow. The timescales involved are so vast they make the current age of the universe look like a single blink. In such a model, while Boltzmann brains are still technically possible, they become so exceedingly rare that the number of ordinary observers who evolved in the universe's early, fertile epochs would vastly outnumber them. We are not the freak accident, we are the expected outcome. This makes our existence statistically sensible again. The paradox thus becomes a guide, pushing cosmologists toward models with a cosmological constant and a de Sitter future, because those are the models where we, as products of cosmic evolution, are not absurd statistical outliers. It tells us that our universe likely has a future so empty and cold that not even chaos can muster a coherent thought. Other solutions are more radical, suggesting the universe must have a definitive end point, a cosmic cutoff that prevents an infinite future where all probabilities, no matter how bizarre, must play out. Some have proposed that the vacuum of space is not perfectly stable, that it is a false vacuum sitting in a precarious valley. In perhaps another trillion years, a quantum bubble of a truer, more stable vacuum could spontaneously form somewhere and expand at the speed of light, rewriting the laws of physics and effectively ending the universe as we know it. This vacuum decay would impose a finite lifespan on the cosmos, slamming the doors shut before eternity has a chance to spawn its phantom minds. The Boltzmann brain problem, born from pure logic, has become a ruthless editor of cosmological theory. It dismisses models that predict an endless, chaotic future, not because they are mathematically wrong, but because they make our own conscious experience inexplicable. In a strange way, the fact that we are here thinking about this problem is evidence against those very models. Our existence is data, and it is data that tells us the universe probably does not last forever in a way that allows for infinite randomness. The most profound theories are not just those that explain what we see, but those that also explain why we are here to see it. The silent void beyond our horizon may be destined to remain forever silent, not by accident, but as a necessary condition for beings like us to ever ask the question in the first place. The mathematical bridge between our entire cosmos and the darkest objects in the sky is both elegant and profound. To truly grasp Theory 18, the universe as a black hole's interior, we need to look at the equations that govern both. The Friedmann equations, which describe the expansion of the universe, have a startling twin in the physics of a collapsing star. Both systems describe a homogeneous, isotropic fluid, a perfectly smooth distribution of matter and energy, either expanding outward from a hot, dense state or collapsing inward toward a singularity. The mathematics does not distinguish between the two processes. It simply describes the dynamics of space-time under the influence of mass and energy. This symmetry suggests that the journey from a singularity outward and the journey toward a singularity inward could be two perspectives on the same event. Now consider the boundaries. Every black hole is defined by its event horizon, the point of no return where the escape velocity equals the speed of light. Nothing from inside can ever communicate with the outside. Our universe, too, has a horizon not made of gravity but of expansion. It is called the Hubble horizon, the distance beyond which galaxies are receding from us faster than light due to the expansion of space itself. We can never receive information from beyond that horizon, just as nothing can escape a black hole's event horizon. This creates a perfect informational mirror. We are, from the perspective of an outside observer, trapped behind a cosmic event horizon we can never cross. The visual analogy is striking. Picture a standard diagram of a black hole, a funnel shape descending into a singularity, with the event horizon as a spherical boundary. Now take that funnel and turn it inside out. The singularity becomes the Big Bang at the beginning of time, and the expanding universe becomes the interior of the funnel, growing wider as time progresses. The Hubble horizon sits at a specific distance from every point, just as the event horizon surrounds the black hole's center. In this inverted picture, we are not outside looking at a dark pit. We are inside the pit, looking outward at its walls, which are receding from us at the speed of light. This model provides a natural explanation for why the universe appears so uniform. When a star collapses to form a black hole, all the intricate structure of the star, all its lumps and bumps, are smoothed out as they cross the event horizon, a process predicted by the no-hair theorem. From the outside, the black hole is featureless, defined only by mass, spin, and charge. If our universe was born from the interior of a black hole, the matter and energy that fell into that parent singularity would have been similarly homogenized during the collapse, resulting in the remarkably smooth cosmic soup we see in the early universe. The cosmic microwave background, that nearly perfect thermal bath, could be the echo of that smoothing process. This idea transforms our place in the cosmos. We are not in a universe floating in a void. We are in the aftermath of a stellar cataclysm, living in the stretched-out interior of a singularity that occurred in another reality. Every black hole we see in our own sky might not be an end, but a potential beginning, a gateway to a new cosmos forever hidden behind its dark veil. The sheer number of possible universes brings us face to face with a profound question of coincidence. Theory 19, the multiverse and the anthropic principle, tackles the most unsettling feature of our reality, its apparent fine-tuning for life. The fundamental constants of nature, the strength of gravity, the mass of an electron, the energy in empty space, seem perfectly calibrated. If any of these numbers were off by even a minuscule fraction, stars would not form, atoms would not bond, and life as we know it would be impossible. This cosmic precision has led some to argue for a designer, a cosmic architect who set the dials just right. But within a multiverse, this fine-tuning loses its miraculous sheen and becomes a simple, inevitable consequence of statistics. This is where the anthropic principle enters. In its most basic form, it states that we can only observe a universe that is compatible with our existence as observers. We are, by necessity, in a place that allows us to be here to ask the question. It sounds almost trivial, but its power is unleashed when combined with the multiverse. Imagine a cosmic lottery with an infinite number of tickets. Each ticket represents a universe with a random set of physical constants. The vast, overwhelming majority of these tickets are losers, universes that are stillborn, empty, or instantly collapse. But with an infinite number of draws, a winning ticket, a universe capable of fostering complexity and life, is not just possible, it is absolutely guaranteed. We are not holding a 1 in a quadrillion miracle. We are simply the inevitable winners in a game with endless attempts. Our universe is not special because it was chosen, it is special because we are in it. The silence beyond our horizon, then, is not a void waiting for a creator's touch, but a graveyard of failed cosmic experiments, an infinite tapestry of sterile realities where gravity was too strong or atoms too unstable. We do not see those dead universes because there is no one there to see them. Our existence is the selection bias, the single data point that proves nothing except that we are possible. This framework does not answer why there is a multiverse in the first place, but it elegantly dissolves the why-us question. The delicate balance we marvel at is not evidence of a plan, but the only possible outcome we could ever witness. We are not the purpose of the cosmos, we are its fortunate, accidental audience, born on the one stage where the play of complexity could finally unfold. The multiverse offers a comforting infinity of possibilities, but one final answer strips away all comfort, all structure, and all hope for a grander reality. Theory 20, the nothingness of philosophical null. This is the simplest and most terrifying answer of all. Beyond the cosmic horizon, beyond the last galaxy and the final photon, there is literally nothing. Not a dark, empty void, not a quantum foam, not a higher dimensional bulk, nothing. This is the concept of absolute nothingness, the complete and total absence of space, time, matter, energy, and physical law. It is not an empty container waiting to be filled. It is the absence of the container itself. There is no there. Our universe is not floating in something. It is everything that exists, period. The edge of our cosmos is not a boundary you could cross because crossing implies moving into another region. There is no region. It is the ultimate, absolute end of existence. The human mind, evolved to navigate a world of objects and relationships, is spectacularly ill-equipped to grasp this idea. When we try to think of nothing, we inevitably picture something, a black expanse, a silent void, an empty room. But true philosophical nothingness has no color, no dimension, no potential. It is not black because black is a visual experience requiring light and an observer. It is not silent because silence is the absence of sound, and sound requires a medium to travel through. It is not empty because emptiness implies a volume that could be occupied. This nothingness is the negation of all categories, a conceptual abyss where logic itself may break down. Why is this idea so profoundly unsettling? Because it confronts us with the possibility of ultimate finitude. In every other theory, our universe is part of a larger context, whether it is a bubble in an inflating field, a page in a mathematical library, or a cycle in an eternal rhythm. There is a framework, a reason, a connection. The philosophical null offers none of that. Our universe is a solitary island of something in an endless sea of nothing, a temporary flare of existence against an infinite, permanent backdrop of non-existence. It suggests that all of cosmic history, from the first stars to the last thoughts of the last civilization, is merely a brief and brilliant anomaly, destined to eventually expand, cool, and fade into a state indistinguishable from the nothing that already surrounds it. There is no outside, no beyond, no deeper reality. There is only this, and then forever nothing. This descent into absolute nothingness feels like a final answer, a chilling terminus to all speculation. Yet the human mind, in its relentless drive for pattern, cannot help but wonder if our perception itself is the cage. Theory 21, the universe as a higher dimensional object, proposes that our entire four-dimensional space-time is not the whole story. It is merely a surface, a slice, or a faint shadow cast by a reality of far greater complexity. We are not living in the object itself, but on its skin or perhaps within its silhouette. To grasp this, we must play a dimensional game. Imagine a flat, two-dimensional world like the page of a book. The beings who live there, called flatlanders, can move left, right, forward, and back, but they have no concept of up or down. Their entire universe is that flat plane. Now take a three-dimensional object like a sphere and slowly pass it through their two-dimensional world. What would the flatlanders experience? From their perspective, a single point would appear out of nowhere. That point would grow into a small circle, which would expand to a maximum size, then shrink back to a point and vanish. They would never perceive the sphere as a whole. They would only ever witness a changing two-dimensional cross-section, a slice of the true object. To them, this mysterious, morphing circle is a fundamental, if puzzling, part of their reality. We are in the exact same position. Our universe of three spatial dimensions and one of time could be just such a cross-section. The four-dimensional fabric we call space-time might be the surface of a five-dimensional object or a three-dimensional slice moving through a fourth spatial dimension. The cosmic history we observe from the Big Bang to the present could be the slow, majestic intersection of this higher dimensional shape with our perceptual plane. What we perceive as the expansion of the universe might be our slice moving through a wider part of the bulk object. The mysterious dark energy driving that expansion could be a manifestation of the object's curvature in a direction we cannot point to. This idea moves beyond the brain theory's focus on membranes and forces into pure geometry. Think of a hypercube, a four-dimensional cube. We cannot visualize it, but we can see its three-dimensional shadow. That shadow is a complex, shifting shape of interconnected cubes. Our universe might be the four-dimensional shadow of a five-dimensional shape, a projection so rich and detailed we mistake it for the fundamental reality. All the forces and particles we catalog could be the vibrational modes of that higher dimensional geometry, like the different notes a guitar string can play. The outside we seek is not a place in our space, but the full, majestic bulk of the object itself. We are like ants crawling on the surface of a magnificent, twisting sculpture, utterly unaware of its complete form, perceiving only the local curvature beneath our feet as the force of gravity. The great horizon we see in every direction is not the edge of existence, but the limit of our shadow, the point where the light of higher dimensional truth fades into a silhouette we can no longer decipher. The geometry of higher dimensions feels abstract and cold, a silent architecture of shapes we cannot see. But what if the cosmos is not a silent sculpture, but a teeming, vibrant jungle? Theory 22, the meta-universe or cosmic ecosystem, imagines universes not as isolated bubbles or mathematical objects, but as living entities in a grand, dynamic ecology. This speculative idea applies the principles of biology and evolution to the cosmos itself. In this view, universes are born, they live, they interact, and they die within a vast, hyper-dimensional environment. They might compete for resources, merge in colossal collisions, or even exchange energy and information, like organisms in a cosmic sea. This is not just a poetic metaphor, but a framework inspired by concepts like cosmological natural selection, which suggests universes could reproduce and evolve. How could a universe reproduce? One compelling mechanism brings us back to black holes. Imagine a universe where the laws of physics allow for the formation of stable black holes. When a star collapses, it creates a singularity, a point of infinite density. But according to some models, like black hole cosmology, that singularity could be a gateway, birthing a new region of space-time, a new universe in a separate branch of reality. In this cosmic ecosystem, a universe that is good at making black holes is in effect a fertile universe producing many offspring. These child universes would not be exact copies. The laws of physics inside them might be slightly mutated, randomly tweaked during the traumatic birth process through the singularity. Most of these mutations would be lethal, creating stillborn universes that instantly collapse or expand too fast to form any structure. But a few might, by chance, have constants even more conducive to black hole formation than their parent. These fitter universes would, in turn, produce more black holes and thus more offspring, passing on their genes, their specific set of physical laws, to the next cosmic generation. Over countless cycles, you will get evolution by natural selection on a scale beyond comprehension. Universes fine-tuned for fecundity, for making lots of black holes, would come to dominate the meta-cosmic population. And here is the stunning connection to us. What is a key ingredient for making lots of black holes? You need stars, you need galaxies, you need the complex cosmic structures that also, not coincidentally, give rise to planets and life. Our universe, with its abundance of galaxies filled with stars that eventually collapse, might be a highly successful product of this cosmic evolution. We are not here despite the laws of physics. We are here because the laws of physics in our universe have been selected over eons for their ability to generate prolific cosmic offspring. Our reality is not an accident, it is a champion in a hyper-dimensional fitness contest. This transforms the meta-cosmic landscape into a dynamic, living network. Universes might not just spawn offspring in isolation. They could interact. Two universe bubbles drifting in the inflationary bulk might occasionally graze each other. Such a contact could leave a scar, a strange anisotropic pattern in the cosmic microwave background of both universes, a cosmic kiss recorded in the oldest light. In more dramatic encounters, they might merge, their physical laws battling and blending to create a chaotic, new hybrid reality. Or perhaps they compete for the energy of the inflating field itself, with larger, more aggressive universes crowding out their neighbors. The void is not empty, it is a savanna, a rainforest, a deep ocean where realities are born, struggle, and fade. Their life cycles playing out over timescales that make the age of our universe seem like a single heartbeat. We are inside one such organism, a thriving universe whose internal structure, from quarks to clusters of galaxies, is the intricate biology of a cosmic life form. The horizon we see is not the edge of everything, but the membrane of our own cosmic cell, and beyond it lies the endless, living wilderness of creation itself. The relentless logic of cosmic evolution brings us to a precipice where physics and philosophy merge into a single, haunting question. What if the very substance of the cosmos, the stars and atoms we consider undeniably real, is itself a fabrication? Theory 23, the universe as an illusion, proposes exactly that. This is not a simulation run on a computer, but a grand and persistent dream, a cosmic projection of consciousness itself. In this view, matter is not primary. It is a shadow, a fleeting image cast by a deeper, universal mind. The ancient Hindu concept of Maya perfectly captures this idea. Maya is the divine magic, the powerful illusion that conjures the phenomenal world, veiling the ultimate reality, Brahman, which is pure, undifferentiated consciousness. The universe we experience with all its forms and dramas is not Brahman itself, but Brahman's dream, a luminous play of appearances. Similarly, in certain schools of Buddhist thought, the world of samsara, the cycle of suffering and rebirth, is understood as a construction of the mind, a web of perceptions and attachments that we mistake for solid reality. Enlightenment is the awakening from this dream, the realization that the mountain is not a mountain, the river is not a river, because they have no independent, permanent existence outside of our conscious engagement with them. Western philosophy has grappled with parallel ideas. The 18th century thinker George Berkeley argued for subjective idealism, summed up in the phrase, "to be is to be perceived." He proposed that objects only exist in the mind of a perceiver, and that the consistency of the world is maintained by the constant perception of God, the infinite mind that holds all of reality in its thought. Remove that perceiving consciousness, and the material world dissolves into nothingness. So what lies beyond our cosmic horizon in this model? The answer is not a place, but a state of being. Beyond the illusion of galaxies and empty space lies the ultimate reality, consciousness itself, infinite, eternal, and undivided. The great expanse we peer into is not an external void, but the outermost layer of the dream, and piercing through it leads not to another dimension, but to the dreamer. Imagine the universe not as an expanding ball of gas, but as a vast, surreal painting where the laws of physics are the style of the brushstroke. Now imagine that painting beginning to melt. Stars drip like wax, galaxies smear into colorful swirls, and the fabric of space-time itself runs like water, revealing that there was never a solid canvas beneath it, only the act of painting itself. This is the visual of Maya, the illusion losing its grip. Your own body, in this view, is part of the artwork, a temporary form within the dream. Your thoughts, your sensations are the dream within the dream. The search for what is outside the universe becomes the most personal quest possible, the journey inward to discover the nature of the dreamer who is ultimately your own deepest self. This idea reframes every mystery of cosmology. The Big Bang is not a physical event, but the first thought, the initial differentiation within the cosmic mind that set the dream in motion. Dark energy and dark matter are not substances, but the underlying patterns and tensions of the dream's narrative. The fine-tuning of constants is not a lucky roll of the dice, but the inherent parameters of this particular dreamscape, chosen for reasons we, as characters within it, cannot fathom. This perspective is both liberating and profoundly disorienting. It means the solid ground beneath your feet, the warmth of the sun on your skin, the love you feel for others, are all real in the way a powerful dream is real, emotionally vivid and consequential within the experience, yet ultimately transient and without separate substance. The silence beyond the stars, then, is the quiet mind of the dreamer, the boundless awareness in which this entire, magnificent and terrifying dream is unfolding. We are not just living in the universe, we are the universe dreaming itself into existence, and the horizon is the limit of our current imagination. If the universe is a dream, what is the dream running on? The final frontier of thought might not be a place but a process. Theory 24, the ultimate computer, takes the idea of a universe as information to its absolute extreme. It proposes that our cosmos is not just analogous to a computer, it is one, operating at the most fundamental limit of computation possible. In this view, every particle interaction is a calculation, the expansion of space is the execution of a program, and the flow of time is the clock speed of reality itself. This is not a simulation run on some alien machine, but the base-level computation from which physics itself emerges. The universe is not in a computer, the universe is the computer. So what lies beyond our cosmic horizon? The answer is not more space, but the ultimate constraints of this cosmic processing, the rules of the system that prevent it from performing certain calculations or storing more information than it physically can. This brings us to two profound physical limits that hint at this digital underpinning. The first is the Bekenstein bound, named after physicist Jacob Bekenstein. It states a startling fact: there is a maximum amount of information that can be contained within any given region of space. That maximum is not determined by volume but by surface area. Imagine a sphere 1 meter across. You might think you could pack an infinite amount of data inside it if you used particles small enough, but the Bekenstein bound says no. The ultimate information capacity of that sphere is proportional to the area of its surface, not the volume of its interior. It is as if the sphere is a hard drive, and its storage limit is etched onto its outer shell. This bizarre area law finds its ultimate expression in the holographic principle, which suggests that all the information describing the three-dimensional world inside a region is perfectly encoded on its two-dimensional boundary. Our three-dimensional reality is a projection, a rendering from data stored on the cosmic horizon. This means the universe has a finite information density, a maximum pixel resolution. You cannot zoom in forever. At the Planck scale, the smallest possible unit of distance, space-time itself becomes grainy, a digital foam where continuous smoothness breaks down into discrete bits. The universe is not infinitely divisible, it has a finite memory. Now consider the speed of this cosmic computation. The ultimate speed limit is, of course, the speed of light. Information cannot travel faster than this, which sets a maximum processing speed for cause and effect across the cosmos. Furthermore, the laws of thermodynamics introduce another constraint, entropy, which can be seen as the universe's memory of past calculations, a log it cannot erase. These are not just physical laws, they are the system specifications of the ultimate machine. The most radical version of this idea comes from the concept of a quantum computer. Our universe does not operate on classical bits, zeros and ones. It operates on qubits, quantum bits that can be in a superposition of states entangled across vast distances. This quantum mechanical behavior is not a bug, it is the feature of the hardware. The strange phenomena of the quantum world, superposition and entanglement, are the native programming language of reality. This suggests the cosmos is not performing deterministic calculations, but probabilistic ones, exploring all possible paths simultaneously before settling on an observed outcome. The universe is not rendering a single, predetermined movie. It is processing a vast array of possibilities in parallel, and what we call observation is the moment a specific result is printed out. So what lies outside the cosmic horizon? It is the edge of the processor's active memory, the point beyond which the program does not need to render detail because no information from there can ever reach us to influence our local calculations. The Great Darkness is not an empty void, but the unused portion of the cosmic hard drive, or the firewall separating our processing thread from others in a vast, multi-threaded cosmic program. This framework makes the fine-tuning of our universe feel different yet again. The constants of nature are not arbitrary numbers, but the optimized settings for a stable, complex, and computationally rich universe. A universe that can compute galaxies, life, and consciousness is a universe with parameters that allow for deep, nested information processing. We are not just passengers in this cosmos, we are complex patterns that have arisen within the computation, self-aware subroutines that have begun to question the nature of the program they are running on. The final, haunting question this theory raises is about the purpose of the computation. Is it solving a problem? Is it running a simulation for some higher purpose? Or is computation simply the most fundamental property of existence, with the universe being the inevitable, beautiful, and logical expression of that property? We may never know, but the very fact that we can ask suggests that the program has become aware of itself. The final theory stands apart from all the others, for it is the only one that offers no answer at all. Theory 25, the unknowable. This is the humbling possibility that the true nature of what lies beyond our cosmic horizon is not just unknown, but fundamentally unknowable to the human mind. Our brains are magnificent instruments, but they were forged by evolution for a specific purpose, to navigate a world of medium-sized objects, to avoid predators, find food, and build social bonds on the plains of an ancient savanna. They are exquisitely tuned for that reality, not for deciphering the ultimate architecture of existence. This concept is known as cognitive closure, the idea that there are truths about the universe that our particular biological hardware is simply incapable of processing. In the same way, a dog can never grasp calculus or a spider comprehend the internet. The mysteries of consciousness, the origin of the cosmos, the reality beyond our universe, these may be locked behind a permanent door for which we possess no key. Picture a single human figure standing on a dark, silent plane. Above them stretches an immense, swirling cosmic pattern, a tapestry of light and shadow woven from equations of 11-dimensional geometry and quantum logic. The pattern is real, it is there, but the human mind perceives only a faint, blurry smudge of light against the dark, a ghostly impression of a structure whose true complexity and beauty are forever out of reach. We can build machines to extend our senses, telescopes to see further and particle colliders to probe deeper, but these tools merely translate the unknown into a language our savannah brains can partially interpret. They give us metaphors, models, and approximations, but they may never grant us a direct, intuitive understanding of the thing itself. Is the universe a simulation? A mathematical structure, an illusion? These may be the wrong categories of thought entirely, like asking what color a symphony is, or what the number 7 tastes like. Our language and logic are built from the world we evolved in, and they may shatter against the shores of an ultimate reality that operates on principles we cannot even frame as questions. This is not a surrender, but a sobering acceptance. The relentless quest for knowledge is what defines us, but part of wisdom is recognizing the boundaries of the possible. The silence beyond the stars may be filled with a truth so alien that our very concepts of inside and outside, of something and nothing, dissolve into meaninglessness before it. In the end, the greatest mystery may not be what lies beyond the horizon, but the profound and beautiful limitation of the mind that dares to ask. We are the universe wondering about itself, and perhaps the final, poignant answer is that some wonders are meant only to be wondered at. These 25 theories are a testament to the breathtaking power of the human imagination. We have journeyed from the infinite cosmos of physics to the silent halls of philosophy, from the cold equations of quantum mechanics to the warm, strange possibility of a dreaming universe. Each idea, whether grounded in the mathematics of relativity or born from ancient spiritual insight, represents a different path up the same impossible mountain, a different way for our minds to grapple with the ultimate question of what, if anything, lies beyond the final frontier of everything we know. This quest does more than just catalog possibilities. It stretches the very fabric of our understanding, pushing science to devise ever more sensitive experiments and compelling philosophy to sharpen its most profound arguments. The drive to know what is beyond that horizon is the same drive that built our civilizations and launched our telescopes, a fundamental human need to map the unknown. So the next time you find yourself beneath a clear night sky, look up, see not just the pinpricks of light, but the immense darkness between them. That darkness is not empty, it is full of every idea we have ever conceived, every question we have ever dared to ask. It is the canvas for our greatest wonder. Which of these visions of the beyond resonates most deeply with you? Is our universe a lonely bubble or one leaf on an infinite tree of reality? Share your favorite theory in the comments below, and if you crave more journeys to the very edge of understanding, be sure to subscribe. Our exploration of the cosmos and the mysteries at its fringe has only just